What if I told you there's a place in the universe where almost nothing exists? A region so vast that the Milky Way could easily fit inside it thousands of times. Today we're traveling to one of the greatest cosmic mysteries, the Great Void. In the large-scale structure of the universe, matter isn't spread evenly. Galaxies cluster along filaments and sheets, and between them lie vast regions with very few galaxies, known as voids. These voids can span tens to hundreds of millions of light-years across. A void isn't perfectly empty. It still contains matter, dark matter, some galaxies, but its density is much lower than the cosmic average. These underdense regions are critical for understanding how the universe evolved. Located about 700 million light-years away from us in the constellation Boötes, the Boötes void is a roughly spherical region whose diameter is around 330 million light-years, 100 megaparsecs, one of the largest known voids in the observable universe. To put that in perspective, within its volume, astronomers expected to find perhaps around 2,000 galaxies based on the typical density of galaxies in the universe. Instead, they found only about 60 galaxies, a dramatic drop. It was discovered in 1981 by Robert Kirshner and his team during a galaxy redshift survey. The discovery of such a gigantic hole shocked astronomers. So how did such a vast emptiness come to be? In the early universe, quantum fluctuations created regions of slightly higher and slightly lower density. Over billions of years, gravity pulled matter into the denser areas, leaving the less dense patches even emptier. One plausible scenario is that several smaller voids merged to form this supervoid, analogous to bubbles merging in foam. The Boötes void might be the result of this kind of hierarchical growth. Because voids contain less matter and fewer galaxies, they also evolve differently than dense regions, offering a kind of pristine laboratory for cosmology. The Boötes void isn't just a curiosity. It carries deep implications. Because voids are so underdense, they amplify effects tied to dark energy, cosmic expansion, and even neutrino physics. For example, studies of the cosmic microwave background, CMB, and large-scale structure show that some voids correlate with cooler spots in the CMB, pointing to the so-called Sachs-Wolf effect, where photons lose energy climbing out of underdense regions. Another mind-blowing fact: if humanity were located at the center of such a void, the night sky and our understanding of galaxy distribution could be drastically different. We might have discovered other galaxies much later because fewer lie in view. Imagine our Milky Way residing inside a void. The lower density of matter would influence local expansion rates of space. Some researchers suggest that such a scenario could help resolve the Hubble tension, the mismatch between different measurements of the universe's expansion. Even though we aren't sure we sit in one of the largest voids, the possibility opens up profound questions about our map of the universe and how typical our cosmic location is. Future surveys and space telescopes like Euclid, ESA, and Nancy Grace Roman Space Telescope aim to map billions of galaxies and voids with unprecedented precision. By doing so, they'll use voids as cosmological probes to measure dark energy, neutrino mass, and the fundamental structure of space-time. By studying the emptiest parts of the cosmos, we may discover some of the universe's greatest secrets. The Great Void reminds us, even in the cosmic wilderness, what isn't there tells a story just as powerful as what is. If you found this journey through emptiness inspiring, hit like, subscribe, and ring the bell, because together we'll keep venturing to the farthest, most mysterious corners of the universe.